Welcome back to Math 103. This is video number 22 on growth and finance. Our task right now is to go back to an old example where we computed explicitly that a certain annuity has future value $6,632.98 and check that our newly acquired formula for that future value, our shortcut formula, really does compute the value that it's supposed to. Here the payment amount is $1,000. The interest rate we're given is 4% per year, and the crucial thing we have to understand is that n here, this n is counting the number of payments. N is not counting the highest exponent, n is counting the number of payments, and there are 6 of them. All we need to do is plug in the values for PMT, I, and n, and see what happens. Keeping in mind order of operations, we have to compute this numerator first, before we then divide it by 0.04. It's a common thing for students to make some kind of an error involving order of operations when they compute using this formula. We find that this expression works out to be 6.63298. So at the end, how much is payment times this funny expression? It's $1,000 times 6.63298. This is not exactly a growth factor in the sense in which we've used that term, but it functions similarly to one. Ultimately, we find out that if $1,000 is the regular payment amount, then $6,632.98 is the total. So this formula has taken into account all the information that's been given. This is the final result. Lo and behold, our formula gave us the same answer as working it out the long way. That's really good news, because now, from now on, we're allowed to use this formula instead of working out these future values the long way. Now we're ready to work through a very important practical example. Everyone should know this. Everyone should understand the consequences of the computations we're about to do. Here goes. Suppose that at the end of every year, starting at age 25, you invest $3,000 in an IRA. That's an individual retirement account. This account has an APR, let us say, of 7% compounded annually. Right now, it would be difficult to find 7% for your investments, but in the larger historical scheme of things, that's not such an unrealistic number. Interest accrues at the end of each year on money which has been in the account all year long. That sentence is just saying what we've been saying in every example thus far. Right? You're going to deposit money at the end of the year. It will have to sit there all the way until the end of the next year before it starts earning interest. We can ask, how much will the investment be worth at the end of the year when you are 65? Since you're making regular equal payments, $3,000 a year every year, and you're asking what do all those payments accumulate to in the end, this really is the future value of a fixed deferred annuity. It really is an annuity because we're making regular payments, equal payments of $3,000 every year, and therefore we are, in fact, allowed to use this formula as long as we plug the right inputs into it. Had this been a one-time $3,000 investment when you were 25, it would be a job for the compound interest formula. Instead, there are many investments of $3,000 each. That's why it's a job for this annuity formula. Before we start plugging numbers into this wonderful shortcut formula, it's very important to understand what it's a shortcut for. It's important to understand what is this very long sum that we would otherwise have to compute if we didn't have this formula. If you write out the long sum of all your separate $3,000 investments and what each one will grow into eventually, you'd start with the investment of $3,000 at age 25, see what it grows into, plus the investment made at age 26 and what it grows into by the time you're 65, all the way down to the last deposit that you make at age 65. So let's understand what the first couple of terms in this sum and the last couple of terms look like explicitly. When you're 25, the $3,000 that you deposit then is going to grow at 7% a year, that's the given information in the problem, 40 separate times. From the time that you're 25 at the end of the year until when you're 65 at the end of the year. 40 full years will have passed. That means 40 separate multiplications at the bank by 1.07. The following year, that $3,000 deposited at age 26, well, That $3,000 gets to sit in the bank for 39 years. It gets to be multiplied by 1.07 39 times. So from age 26 until age 65, 39 full years go by. There are 39 separate growths by 7%. This pattern keeps going. Every year there's a new $3,000, and that $3,000 gets multiplied by 1.07 a certain number of times. You get a sum of many different terms that look like 3,000 times 1.07 to the something, and that something keeps dropping by 1 at each step. All the way near the end of this long sum, you can look at the second to last $3,000 you deposit. That's happening when you're 64, and that $3,000 gets to sit in the bank for just 1 year, and therefore earns interest just once. That means it grows from 3,000 to 3,000 times 1.07, or 1.07 to the first power. Finally, the last $3,000 you deposit at age 65 sits in the bank for 0 years. It has no time to earn interest. So that last $3,000 grows into $3,000 times 1.07 to the 0. So just for completeness, we're writing it out in the same format as the other terms. Great. At the end of the day, you really have a sum of many different terms that look like $3,000 times 1.0 to the something. Those somethings range from 40 all the way down to 0. It is very important to be able to carry out that reasoning process that lets you write this sum explicitly, because otherwise it's unlikely that you're going to use the formula correctly. It's also important to remember what's really going on here. There's really a sum of many separate terms, the result of many separate $3,000 investments. Once you've gone through the important process of reasoning out this sum, writing the first couple of terms and last couple of terms, then plugging into the formula is just a computational shortcut. So before going on to the next video, use that formula for the future value of a fixed deferred annuity to compute the total value of your investment at the end of the year when you're 65.